Morning, ladies and gentlemen. Welcome to our gravitation tutorial. Let's take a look at question 1. State Newton's law of gravitation. Now, Newton's law of gravitation only works for point masses, and it says that the force of attraction between two bodies is proportional to the product of the masses and inversely proportional to the square of the distance between the centers of masses. The force acts along the line joining the centers of masses. The underlying words are critical, so you must have the underlying words inside. Now let's take a look at the gravitational field strength. The gravitational field strength is at a point is the gravitational force per unit mass on a small test mass at that point. All right, so this comes from the equation G is equals to gravitational force divided by the mass of the object. All right, and this one comes from the equation that the gravitational force is proportional to the masses, the product of the two masses, and inversely proportional to the square of the distance between the center of mass. Now let's take a look at question 2. The gravitational field strength at the Earth's surface is G. Calculate the gravitational field strength on the surface of a planet which has the same mass as Earth but twice the radius, and half the radius and double the density of Earth. So let's take a look at the first example. Here is the mass of the Earth, and here is the radius of the Earth. So the gravitational field strength in this case will be Gme over Re squared. And basically this is how it's equal to. Now let's take a look at the new one. The new one has the same mass as the Earth but twice the radius. So the radius will be 2Re. So Gme over 2Re squared, right? So this actually what it means is that it becomes a 1/4 of Gme over Re squared. And this means that it's actually 1/4 G. So now let's take a look at the next question. The next question is a planet with half the radius and double the density of the Earth. So the radius is actually half radius of the Earth, and then the density of the Earth, the density will be twice the density of the Earth. Now let's take a look at what happens to the mass of the object if the density is doubled and the radius is halved. So the mass of a sphere will be equals to the volume multiplied by the density. And the volume of a sphere is 4/3 pi r cubed. Now, in this case, the planet's radius is half. So that is half of the Earth cubed multiplied by the density. But the density is twice the density of the Earth. Alright, so this will be 4/3 pi Re cubed density multiplied by 1/8 multiplied by 2. So that's 1/4. So what this means is that the mass will be 1/4 the mass of the Earth. So over here, this is the mass of the Earth, and this is 1/4. So the mass is 1/4 the mass of the Earth. Now, if the mass is 1/4 the mass of the Earth, then the gravitational field strength will be given by G 1/4 of the mass of the Earth divided by half of the radius of the Earth squared. Alright, so this will give us 1/4 multiplied by 4 multiplied by Gme over Re squared, and this gives us just the same value of G. So what this means is that the gravitational field strength of the new planet, which is half the radius and double the density, is the same on the surface as it is on the surface of the Earth. Alright, so this is question 2. Now let's move on to question 3. Consider two fixed point masses of radius r with m and 9m mass separated by a distance d. Determine the distance in terms of d from the 9m mass where a third point mass can be placed such that the third mass experiences no net gravitational force. So this is going to be the neutral point. So how do we solve this question? At the neutral point, the resultant gravitational field strength must be 0. So let the distance to the gravitational neutral point be r1. Now, thinking about it, right, if there's a planet with 9 masses, 9m, the gravitational field must be quite strong. So in order to find the point between the two planets where the gravitational field cancels out, this must be sort of where the point lies. All right, so what we're going to do is that we're going to put over here, this will be R1. Okay, so then this distance will be d minus R1. So let's find out how to balance the gravitational force on the third mass. Okay, so we're going to let the gravitational field strength be 0. So that means to say the gravitational field strength of the 9m mass will be equal to the gravitational field strength of the single m mass. So the gravitational field strength of the 9m mass will be g 9m, which is the mass, divided by r1 squared at that point. The gravitational field strength of the mass m will be g m d minus r1 squared. Okay, so now let's go down to the equation. We follow the steps over here, we cross multiply, and then we solve. I think there are actually two possible solutions to this problem. Okay, I think it's R1 is either 0.75D or 1.5D. Now this 1.5D is rejected because it lies outside of the 2 points, so it doesn't make any physical sense. So the answer will be 0.75D. Okay, now next, on the axis below, sketch the graph of gravitational field strength with distance between the 9m mass and the m mass. Now let's take a look at the gravitational field strength. Here is 9m and here is m. This point here is a neutral point. That means to say everywhere along this side of the neutral point, if you drop a mass, the gravitational field will point this way. So this is the gravitational field direction to the left. And on the right, the gravitational field direction will be to the right of this neutral point. Okay? So a gravitational field direction to the left can be considered as negative, and the gravitational field direction to the right can be considered as positive. So let's start to draw the graph. All right. So the neutral point will be 0.75D. So just estimate and then draw a point about 3/4 of the way towards the right hand side and put down 0.75D. Now over here, this point will have a strong gravitational field and this point will have a weak gravitational field. To the left, the gravitational field has negative values, and to the right, the gravitational field has positive values. So this is how we would draw the graph. Now let's go on to question 4. Consider the Earth to be a sphere of uniform density with this mass and a radius of 6370 km. So we just make sure that we convert that to meters. The Earth spins on the axis with a period of 24 hours, convert to seconds. A mass on the equator is placed on a weighing scale. By considering the forces acting on the mass, determine the apparent value of G due to the rotation of the Earth. So basically what we want to find is what is the weighing scale value. So what is the weighing scale reading? Now the weighing scale reading is going to be N, the normal force on the mass. So let's take a look at how this question is set up. Here is the Earth and here is the equator. The Earth spins around the equator, okay, once every 24 hours. Okay, so over here there is a weighing scale, and on top of the weighing scale, this is a weighing scale, and on top of the weighing scale sits a mass M. All right, sits a mass M. Oops. Okay, so this is the mass M. So the question is, what is the weighing scale reading? What is the weighing scale reading? So let's look at the forces acting on the mass M. So supposing the weighing scale is over here, all right, there will be two forces acting on the mass M. The first force will be the weight, and the second force will be the normal force. together the weight and the normal force will provide the centripetal force. So since the acceleration is towards the Earth, then we can write down the equation mg minus n will be equals to the centripetal force. For the centripetal force, in this case, we use mr omega squared. Okay, so we have mg minus n equals to mr omega squared. And then we'll fill in the values. Now, the value of g is obtained by g times the mass of the Earth, 5.97 times 10 to the power of 24, divided by the radius of the Earth, 6370 times 10 to the power of 3 squared, minus the normal force equals to the m multiplied by r. The r is 6370 multiplied by 10 to the power of 3, then omega squared. That will be 2 pi divided by 24 times 3600 and squared. Alright, so let's work out the values here. That will give us m multiplied by 9.81 minus n equals to m, and this will give us n equals to m multiplied by 9.776, or basically that the normal force, the reading on the scale, will be 9.77 times of the mass, 9.78 times of the mass. Okay, so hence the apparent value of g will be 9.78, because when you put an object on the weighing scale, all right, it doesn't read 9.81 times of the mass, it reads 9.78 times of the mass. So the apparent value of g will be 9.78. Now what's happening is basically we're taking the acceleration, the gravitational field strength of the Earth, this is the value of g, and this is the acceleration due to gravity. This is centripetal acceleration. So g minus ac, okay, will give us the apparent value of g. Now, what happens if the Earth spins faster and faster? When the Earth spins faster and faster, the centripetal acceleration required will increase. So you can kind of imagine a time when the Earth spins so fast that the centripetal acceleration is 9.81, in which case we'll all start floating, because the the gravitational force is just able to keep us on the surface of the planet, so the normal force will be 0. Okay, and that's question 4. Now let's take a look at question 5. Define gravitational potential at a point. Now gravitational potential at a point is the work done by external force, but in bringing a small test mass from infinity to that point without a change in the kinetic energy of the mass. So this comes from the equation, all right, KE1 plus GPE1, this is the infinity. So the object starts at infinity and then is brought to the point over here, point 1. So we write KE infinity plus GPE infinity plus the work done by the gravitational force will be KE1 plus GPE1. Now, since there's no change in KE, so there's no change. The K can be cancelled on both sides. The GPE at infinity is defined to be 0. All right, so therefore the work done by external force will be m phi, where phi is the gravitational potential. So this means that the gravitational potential will be the work done by the external force divided by mass. So basically it's the work done per unit mass by an external force to bring a small test mass from infinity to the point without a change in KE, gives you the gravitational potential. Now, why is the gravitational potential negative? Now, at infinity, the gravitational potential has a value of 0. Now, since the gravitational force is attractive, so when you bring an object closer to the planet, then the work done by the external force must be negative. And since the work done by external force is, the gravitational potential, the work done per unit force, but work done by external force per unit mass is the gravitational potential at a point. If the work done is negative, then the gravitational potential must also be negative. Let's move on to question 5c. The diagram shows 2 points x and y at a distance of L and 3L from the center of the Earth. The gravitational potential at x is minus 8 kilojoules per kg. So this will be gravitational potential at x. Calculate the potential energy of a 3 kg mass at x. So we're going to use the formula gravitational potential will be mass multiplied by the the GPE will be the mass multiplied by the gravitational potential. This will be 3 multiplied by minus 8 times 10 to the power of 3 joules. That will be minus 2.4 times 10 to the power of 4 joules. So basically, that's how much gravitational potential energy it has. Is a negative number as expected. Now, what about the potential energy of a 3 kg mass at point y? You notice that they did not give us the potential at y, but they gave us instead the new distance from the center of the Earth. Now, in order to find the new distance from the center of the Earth, we can use the formula phi is equals to minus gm over r. Now, that means that if the distance is increased to 3 times that of what it was before, then the value of the gravitational potential will drop to 1/3 of the previous gravitational potential. All right, so if r prime is 3r, then phi prime will be 1/3 of phi. So we can do it in several different ways. Okay, so the easiest way to do it will be the gravitational potential energy at y will be 1/3 of the gravitational potential energy at x, because since the gravitational potential dropped to 1/3, so that will be 1/3 multiplied by 2.4 times 10 to the power of 4. So this will be this should be a negative number, right? That will be minus 8 times 10 to the power of 3 joules. Okay, so that will be the potential energy of an object at point y. Now, calculate the work done on a 3 kg mass by an external force when it is moved from x to y at constant velocity. So basically, what we're going to use is the KE of x plus the GPE of x plus the work done to move the object from x to y will be the KE at y plus the GPE at y. So since the kinetic energy is constant, we'll cancel out both sides. The GPE at x will be negative 2.4 times 10 to the power of 4. And the work done is W. The GPE at y is negative 8 times 10 to the power of 3. So then the work done will be, you just add the two numbers together. So 1.6 times 10 to the power of 4 joules. So the work done by external force is positive. Since you are moving further away from the planet, so you're going to have to do positive work since the force and the displacement are in the same direction. Right, so this is the force and this is the displacement from x to y are in the same direction. Now relate the work done to the change in potential energy. Since the velocity is constant, the kinetic energy of the 3 kg mass does not change. By conservation of energy, the positive work done by the external force equals to the increase in the gravitational potential energy of the system. So the keywords here will be the positive work done by external force equals to the increase in the gravitational potential energy. Right? So this is the keywords here. And that's all for question 5. Now let's take a look at question 6. Derive an expression for the escape speed of an object launched from the Earth's surface in terms of the radius of the Earth and the gravitational field strength of the surface G. Explain your working. Alright, so in order for us to derive this expression, we shall use the conservation of energy. Now, based on the conservation of energy, the total energy of the system at the surface of the Earth will be equal to the total energy of the system at infinity. So the gravitational potential energy at the surface plus the kinetic energy at the surface will be equals to the gravitational potential energy of the system at infinity plus the kinetic energy of the object at infinity. Now, the formula for GPE will be minus GMM over R, and the formula for KE will be half mv squared. Now, we assume that the KE at the infinity is 0 because we assume that the object has just enough energy to reach infinity and stop. So the object will have just enough energy to reach the surface and stop. Reach infinity and stop. Okay, so that rearranging the equation, we can get the escape speed will be 2 times of gm over r. However, they want us to give an expression in terms of g. So since the gravitational field strength is gm over re squared, we can squeeze in the value of g inside this expression by getting the radius of the Earth outside again. Okay, so because gm over re squared times re is the same as gm over re. Can you see how the algebraic manipulation is done? All right. So the escape speed is therefore v escape is equals to square root 2 times of the gravitational field strength multiplied by the radius of the Earth. Okay, so you can't express your answer in using any other variables because the question does not allow for it. You can only use the variables Re and gravitational field strength G. Okay, now given that the mass of the moon is 7.35 times 10 to the 22 kilograms and the radius is 1.7 times 10 to the 6 meters, calculate the escape speed of a particle at the moon's surface. Now there are two ways to do this. Okay, so since the question earlier has given us, that the escape speed on the moon is equals to square root 2 times of the g multiplied by the radius of the planet. So we can then use this idea. First, we find the gravitational field strength of the moon to be gm over rm squared. So the gravitational field strength of the moon will be 1.696 newtons per kg. So then after that, we can just substitute in these values, okay, into the moon to find the escape speed on the moon will be 2.4 kilometers per second. So it's 2,400 meters per second. Now notice that you can compare this to the Earth's escape speed, which is much higher. The Earth escape speed will be 11.2 kilometers per second. All right, so that's about 5 times more than the escape speed on the moon. All right, now let's take a look at question 7. Now, this is question 7. You notice that there are two objects right now, and there's a third object. So actually, this is 3 objects in this question. So it's two massive objects in the question. Now, if there are 2 massive objects in the question, then basically you have to note that formulas such as G is equals to Gm over R squared, they can't be used directly in order to find the gravitational field strength, because you need to consider 2 different objects. G equals Gm over R squared is only for a single point mass. And now we have 2 masses involved in the equation, so we can't use this directly. Now, let's take a look at the data very carefully. The following data is given: radius of the Earth, radius of the moon, mass of the Earth, and mass of the moon, and distance between the center of the Earth and the moon. So this is the distance between the center of the Earth and the moon. Okay? Now, calculate the net gravitational field strength at the surface of the Earth at point A. Now this net, the word net over here, right, is very critical because it means that there is a combination of different gravitational field from the Earth and the Moon. So let's imagine this point A near the Earth's surface. This is the gravitational field of the Earth, and over here is the gravitational field of the Moon. Okay, so the net gravitational field will be due to the pull from the Earth and the pull from the Moon. Now, you would expect this to be 9.81 or maybe 9.78, but in fact, it is much less than that. Let's take a look. Now, the gravitational field at the surface of the Earth will be given by this one. So this is the gravitational field of the surface of the Earth. This is GE. Okay, this gravitational field of the surface of the Earth. And what about the gravitational field of the Moon? This is the gravitational field of the Moon, GM. Okay, so when you subtract GE from GM, you can see that the number is 9.74. Okay, so there is a very, very small but noticeable effect of the Moon on the Earth, and it is this effect that gives rise to the tides pulling us. You know, high tide and low tide on Earth is due to the Moon's gravitational force on the Earth. Now, at what distance x from the center of the Earth would the net gravitational field strength due to the Earth and the Moon be 0? So this is a neutral point problem, which we have done before. Okay, so I won't go through it too much again. So I'm sure you know how to do the gravitational field strength problems. So this is the Earth, and this is the Moon, and this is the distance from the center of the Earth, x. Okay, this is the total distance, d. So what will happen is that gm of the Earth over x squared will be equals to gm of the Moon divided by d minus x squared. So the hard part is just putting all the numbers inside and using the calculator. Now let's go on to part C. Calculate the net gravitational potential at the surface of the Earth. Remember to include the gravitational potential due to the Moon. So let's take a look at the distance here. This is point A. Okay, this is the Moon. Okay, this distance here is d. And this distance here is the radius of the Earth, RE. So what is the gravitational potential at the surface of the Earth? The gravitational potential at the surface of the Earth will be the total gravitational potential will be the gravitational potential of the Earth plus the gravitational potential of the Moon. Gravitational potential of the Earth will be given by minus gm over r. And what about the gravitational potential due to the Moon? It will be minus gm mass of the Moon divided by d minus re. All right, because this is the distance. This is the distance. This is the distance re. So this is the distance d minus re. Okay, so fill in all the numbers. You get minus 6.23 times 10 to the power of 7 joules per kg, as shown in the answer above. Okay, now let's move on to the next part. Calculate the net gravitational potential due to the Earth and the Moon at the distance x from the center of the Earth. What are they asking for? They're asking for the gravitational potential at the neutral point. They're asking for the gravitational potential at the neutral point. So the gravitational potential at x will be basically equals to the gravitational potential of the Earth at x plus the gravitational potential of the Moon at x. Okay, so this will be minus g me divided by x, because that's the distance from the Earth to that point, minus g m Moon over d minus x. Okay, so that will give us minus 1.28 times 10 to the power of 6. Okay, So the net gravitational potential at point B is minus 3.86 times 10 to the power of 6 joules per kg. Sketch the variation of net gravitational potential along the line joining the surface. Now let's take a look at all the three numbers. Okay, potential at A is minus 62.3 times 10 to the power of 6 joules per kg. Potential at X is minus 3.86 times 10 to the power of 6 joules per kg. And potential at B, which is on the moon, this is 1.28, and this is minus 3.86 times 10 to the power of 6 joules per kg. So if the Earth is over here, here is the Earth, and if the moon is over here, here is the moon, then sketching the gravitational potential will be like imagining that there are two balls pulling down the rubber sheet. Now, because the Earth's gravitational potential is lower, so it pulls the gravitational rubber sheet all the way down. And then the moon is, of course, a smaller, it's an object with a lower with a gravitational potential on the surface is not as low as that of the Earth. So, the gravitational potential sheet, the rubber sheet doesn't go down that deep. So this is the graph that we're going to see. Now, this point here, okay, will be somewhere closer to the moon. The distance, this is the point X, the neutral point. Over here, this is the point A, this is the point B, and this is the gravitational potential at A and B respectively. Okay, so now a projectile is launched from the Earth's surface. Its destination is the moon's surface. Determine the minimum launch speed of the projectile so that it can reach the moon. So if we're going to launch an object to the moon, it must be able to reach this point at the minimum. So the object will rise from the Earth, it will reach the moon, and then after that it will fall towards the moon. So this is the minimum amount of kinetic energy must be able to get it to the neutral point. Okay, the rocket needs to have sufficient energy from the Earth's surface to just reach X. Thereafter, the net gravitational force on the rocket will point towards the moon. So we can always write, the KE at point A plus the GPE at point A will be equals to the KE at point X plus the GPE at point X. Now the KE at point A will give it half mv squared. That is our launch speed. The GPE at point A will be mass multiplied by the potential at A. The KE at point X will be just slightly a little bit more than 0. That means to say it's 0, but it's still moving a little bit. So an infinitesimal speed more than 0. And then the GPE at point X will be the mass multiplied by the potential at point X. Okay, so now let's rearrange the equation. Okay, and we can fill in some of the values. We'll first cancel out the mass over here. Let's cancel out the mass. So half v squared, okay, plus the potential at point A, which is minus 62.3 times 10 to the power of 6, will be equals to the potential at point X, is minus 1.28 times 10 to the power of 6. Okay, so from this we can get the equation V is equals to 11.0 times 10 to the power of 3 meters per second. Okay, so you can see that the velocity at which we need to launch the object is quite close to escape velocity. Okay, so for us to reach the moon, it needs to have this amount of speed at the beginning. Now, do we launch rockets at this speed? The answer is no, because we can't go so fast in the Earth's atmosphere. We have to actually leave the atmosphere first. They travel relatively slowly until we get away from all the air resistance. After that, then we can speed up much faster. Okay, calculate the speed that the object would have as it impacts the surface of the moon. So this is the potential diagram between the Earth and the moon. Okay, so this is a potential diagram between the Earth and the moon over here. Now we notice that as the object reaches the moon, okay, it loses the GPE and then it gains KE. Okay, so we can say that using the conservation of energy, the KE at x plus the GPE at x will be equals to KE on the surface of the moon plus the GPE on the surface of the moon. So the KE at x, previously we said that the object was moving very, very slowly, so it's just 0 plus. And the GPE at x would be m phi x. Then it will be equals to KE on the moon, which is half mv squared, plus the mass, plus the GPE on the moon, which is delta b, phi b. So let's cancel out all the m's again, and then we get phi x minus phi b, okay, will be equals to half v squared. So we can put down phi x is minus 1.28 times 10 to the power of 6 minus 3.86 times 10 to the power of 6 equals to half v squared. So then we can get the velocity at which it hits the moon's surface will be 2.27 times 10 to the power of 3. What does this mean? This means that if your rocket doesn't have any way to slow it down, it's going to hit the moon's surface at a minimum speed of 2.2 kilometers per second. So it's very important to have sufficient fuel to decelerate yourself before it hit the moon's surface. Okay, and that is our end of this video. Our next video will cover circular orbits from question 8 onwards. Thank you for watching.